and has actively contributed to science and communication and faculty development initiatives. His current interests include quantum computing education and research on crypto agility in the post quantum era. Transitioning from academia to startups, he is presently the founder and scientific lead at QuantumX, working at the intersection of quantum technologies, education, and research. We are truly honored to have him with us today. I request Dr. Tabasumara to kindly welcome Mr. Ajmal with a token of gratitude. Thank you, ma'am. I request Mr. Ajmal to kindly take over this session.
Yeah. Audio test. Yeah. No, no, fine. Start with sir, you have to press it. Okay. Yeah. It's working, right? Yes, it's working. Thank you. Okay, let's start. I'm audible, right? Yeah. Yeah. Hello. Hello. This one or this one? Hello. 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 You can use this one. Hello. Yeah. Uh, hello. So I like how many of your faculties like it's a FDP program, but still uh, okay. So many of them are faculty. Like any students who are interested in this domain or like sitting, even if this is an FTP. Okay, no one is there. Okay, so anyone from physics background, like who are teaching physics students? No, everyone is from engineering background. Okay, good. So uh, like uh, like I have been working as a faculty like for 2 years. Then I switched into industry, then to founding my own startup. So it's always good to interact with faculties. So to do research in my own terms, like I preferred, it would be better to work in a startup rather than in an academia, because like to get proper research funding I'll have to be a senior professor. Like it will be more easier if like I started a startup. That's why I like switched from academia to industry. But I still like very much miss teaching in colleges. uh, so I am the founder of QuantumX. So we work mainly on like quantum computing education research, and also in the process of ideation for the software domain. Okay, like we are focusing on post quantum cryptography. So my talk will be like I have been working in the quantum domain for past, like from 2019. Like I have been doing research. My master thesis was on this, and like I have carried out independent quantum computing research. I have given talks on quantum education, and like also like my PhD work is on molecular quantum mechanics. It's not directly related to quantum computing, but it's related to quantum mechanics anyway. So I really like the atomic realm. That's something that I would really like to work on. So what the talk will be focused on, I'll be having three presentation. Okay, so one will be on the post quantum challenges. The second one will be on the physics, especially the work that I did on decoherence, like why it is relevant in the domain of quantum computing, but because it is one of the greatest challenges that we face, especially in the scalability problem. So then the era with respect to quantum computing we are on is NIST, noisy intermediate state. And the one that we are progressing on is to fault tolerant quantum computation. That is something that will be seeing in the upcoming years. So noise and decoherence is like one of the key challenges that we have. And the third talk will be more on the policy level, because uh, there should be policies given. So the challenges, like especially in the Indian context, there are no specific hard and fast rule in the quantum resistant era. But like the National Quantum Mission have been like aggressively funding for research, and like there are very good things happening under the National Quantum Mission. Like four thematic hubs are there. One is in Bangalore, which is in the IISc, and one is based on quantum communication in IIT Madras. Then the other one is on quantum sensing and metrology, and uh, one is in okay. There are four sensing and metrology, and there is one is in IIT Bombay and one is in Delhi. Okay, so let me jump to the talk. So the current cryptographic protocols that we use for banking and all the infrastructure, it relies on unsolvable math problems. Unsolvable as in it will take a lot of computational time to get it solved. That's what it is making them more secure. Like if you have access to very good computers, even that will take a lot of years. Not in the human life, it will get solved. And that's how our banking credential and all is happening now. It's more secure in that aspect. So the thing is that like we have to start now, because with respect to the research, if you don't start early, will not be like the scaling, and will the software development will have its own mismatch. So like I've taken an analogy. So the thing is that the current classical protocols, it will take a lot of years to guess. And the thing is that a quantum computer in the other way, it will have like advantages which you may have heard already in the previous session. Like what are the things that you have? One will be superposition, and there will be quantum entanglement. Then there are physical phenomena like teleportation and all, which is enabling quantum computation. So it'll make quantum computing of like the things that we have less secure with faster computation. So I'll be focusing on the challenges. Okay. So like from the past talks, like I want to know, like is the current quantum computers capable of breaking the encryption that we have, the classical encryption? Like what have you understood? Like I want to know from you. Uh, Please. Like the quantum computers that we currently have, like do they break the protocols? Like
They have gone to certain extent of breaking into some of the protocols.
uh,
Not fully
yeah,
broken.
yeah,
Partially, you can say that some of the rules have been broken. For example, can say that the rules was already broken on quantum computers.
yeah.
And RSA, to certain extent, it is broken, but not fully broken there.
But the thing is that it's still not matured enough to break what we use. Okay, so like my presentation will be more on grounding the hype versus the reality. As sir correctly said, on a partial extent they have like achieved something, but like the number that we need is something like this. For a cryptographically relevant quantum computers, we need a number like this. It's the order of hundred thousands, but we don't have computers like that now. Like it is in the order of thousands. The physics is the bottleneck here, because when we try to solder or bring qubits together, it will interact with each other and it will decohere and it will cause more problems over and over again. So the estimated arrival is like the usual from the usual literature, it's around 10 to 20 years. Some are saying that it will happen faster, but this is something that usually the industries are saying. Some are saying that there are physicists and engineers who says that it will never happen in our lifetime. There are people who are skeptical in that aspect also. But we as academicians and industrialists, we should really work hand in hand together to work ahead. So this is some of the protocols that we use. Like you people are more expert. You may be, especially from the CS and engineering background, you may have heard this more than what I have. Like the RSE and ESE, like which was already mentioned. Like these are the protocols that we use, and with these algorithms like Shor's algorithm and all, like it's theoretically already proven that these things can break. So like this is something that I told before. So it will like the even if we have the powerful supercomputers, the classical ones, it will still take a lot of year to break it, which is how our secrets are secure. And so when we come to the quantum realm, like it will change how we are perceiving this kind of security. So Shor's algorithm, Professor Shor is still available. You may have seen already some of his lectures. Like he have brought something as we know, something that can be solved in polynomial time is being reduced to exponential time to polynomial time. So it will be more linear to solve. So this is something that is the bottleneck here. The stable hardware, we don't have a stable hardware, and so it will impact the encryption protocols. So who need to you have a quantum computers? Quantum secure protocols. So say that the admission data that we use, or say something that should be kept confidential. What is something that should be stored like for 15 to 20 years? What do you think? Some data that should be stored for 20 years. Yes, demographic data is something that we have to store, and the other things that we need to store, like what do you think? Yes, financial data, bank details, details. Then what about election? Like at some point, if the data is leaked, it's a lot controversial topic, but still, if someone knew which person we did vote to, that would be a big controversy. That is something that should be kept secure, and that is why governments and banking sector, they are very much scared whether their secret will be out. There are a lot of things that uh, that causes chaos. That's why they are working on quantum resistant protocols. So, let me make it clear. I don't know whether you have like gone through in that aspect. Like there are certain protocols. Like what do you like understand when we say quantum resistant protocols? Like I don't want to point hands, but like I want to keep it interacting because we have like around 2.5 hours, and like everyone will be asleep by now because it will be technical. So like what do you think when people are saying, companies are saying quantum resistant protocols? Like let's break down the words. Like what is quantum resistant? This side is having less participation for some reason. They are scared about Tabasuma. I don't know. Like so, so there is no judgment here. Like as you know, uh, like I'm very much junior to you when it comes to academic things. That like I won't definitely judge you people, but like please have a free communication. Okay. So so what do you like understand from quantum resistant protocols? Like what do you they cannot be exactly, they cannot be broken with the help of, like as I mentioned before, the cryptographically relevant quantum computers, when they come to power, it should not be broken. Okay. So there are two types of quantum resistance approach that we have. One is easily scalable and one is not. Okay. So I'll be focusing more on the classical protocols in my talk. Like I'll be mentioning them rather than the quantum based protocols where we use quantum physics directly. Okay. The post quantum cryptography, which is like the classical protocols, that is quantum resistant. So when we say about post quantum cryptography, here we use, I'm touching, yeah, I have a laser pointer, but I am still, yeah. So post quantum cryptography, here we, the ones that we are mentioning is basically classical protocols itself. Okay. So there are many cryptographic protocols. One of them are lattice based protocols. This is something that the US government, like when they release guidelines, there is something called as, like we have here DST and Department of Defense, and there are like organizations, something like that, standardization organization. NIST is one of the standardization organization where they like say to use this particular thing, which protocols they have to use. So like even there is something called as Department of War under the US government. It's a weird name to give to a department, but still they have given a guidelines that they will be using post quantum, like classical protocols. Not they will be not be using quantum key distribution. Okay. So yeah. So this is something, the one of the bottlenecks for the classical protocols that we have is the key size is very big. So it will take time. Like when we will get very pissed, like at the point, like if it takes some time for a particular website to say that like what is your like patience threshold like for one browser page to load, like what is so how many seconds can you wait before a web page load? Like, have you ever thought about that? 5 seconds is something, yeah, 3 to 5 seconds. So when we use protocols like this, it will take more time. So that is something like one of the challenges that we have. The whether it's lattice or the like, I'm not an expert in the architecture of these particular cryptographic protocols, but the thing is that it takes a lot of time. Like the PKI, public key infrastructure, it will take a lot of time. That's why like companies are very much hesitant on like migrating to post quantum era. So yeah, these are some of the standards that are recommended, the MLKEM, MLDSA. There are a lot of things I have mentioned a few. Like what the MLKEM, if you are very much interested on cryptography or a professor working on a cryptography, when you read about post-quantum cryptography, you will come across MLKEM definitely. So, and there are, so it is used for mainly establishing secret keys, which is something very much important. And the other one, the MLDSA, is for digital signatures, which we use for identity verification, and then signature SHDSA. So, see, this is the problem. So, the thing is that, sorry, I'm again very much used to point at boards and talking, sorry. Yeah, so the thing is that the RSA key size is 256 bytes, but see, for MLKEM protocol, it's 1184 bytes. Sorry, I said bits, it's bytes. So the problem is that network packets is bigger, it will take time, and also some of the system might break. Okay. So this is why companies are very much reluctant. This is one of the big challenges that we have. See, for elliptical cryptography signature, it's only 64 bytes, whereas MLDSA signature is it's of the order of 3000. So the problem is that digital certificates become larger. That will cause again more chaos for companies. So what we'll do is that, so the approaches that, like when we talk in the industry, so something that we do is that we will like make hybrid protocols, use a mix of post quantum and quantum to migrate post quantum. So like there are like very many places, including IoTs, they are limited by, like, have you seen like IoT sensors? There will be like Raspberry Pi, like I like many engineering faculties may have used. It's very small, and the RAM capacity will be very less for Raspberry Pi and all. So the RAM is a limitation, and it will take, when we use post quantum cryptography and protocols, it will require more hardware capacity. So again, it's an engineering hurdle. So for low power sensors and other systems that we are using. So something that they currently happening, like I have been to, like when we talk with PKI people, so what they are telling is that like we don't have to migrate completely to PQC security for now, but we will mix it, so it will be hybrid. So think about it. So when like, especially like people like have anyone seen the Marvel movies like Ant-Man, or like movies like that? If you are a science fiction movie enthusiast, they have used quantum, the word quantum, very much in every random places which have no connection. So that kind of hype is that even if I'm working in this particular domain, like there is a lot of hype in this domain, which may be controversial. Some may debate that the hype is good. There are like people like in the social space, whether it's Reddit or LinkedIn, there are people who fight a lot in this. You are selling a bubble. Like when when we talk about quantum computing, AI is another bubble. Quantum computing is a newer bubble. Like there are a lot of controversial. And on the other hand, the other extreme end is that quantum computers can solve everything, which is not the case when we like look it in a scientific approach. Okay, so so there is quantum based cryptography, then there is PQC, but where we are currently is something like this. So the current directive is whether it's in the Middle East is aggressively like working on this post quantum cryptography migration, and then countries like Singapore, Malaysia and all in the Southeast Asia, they are also having policies. And also the EU, European Union, and the United States also have their own like policies and directives, which is very interesting if you go through, like, and companies like Visa, Mastercard, like everyone, like they are working on this post quantum migration. So hybrids is something that is working on, and so it's something that we are working, and it will be so. Again, for web certificate, do you know the lifetime now? Like there are like for certificates like getting expired. No, it's around 6 months now. It's around 6 months. So as the technology is advancing like as fast as that, like policies like this will be changed, and there will be like even the web certificates and other policymakers, they have to incorporate quantum concept like this. So this is the comparison. Okay, I have told. So now we are currently on is the hybrid architecture, where we use classical protocols that is currently existing plus the quantum post quantum PQC protocols, which is still classical protocols. No quantum physics is used here. Like we are like when we talk about elliptical cryptography and all those things, they make use of an architecture where it's both difficult to decrypt in using classical attacks or quantum attacks. So QKD is quantum key distribution. This is something that I worked on. Like I worked mainly on QKD rather than PQC. So QKD use protocols like use physical phenomena like entanglement and superposition. I think yesterday's talk covered a lot of concept like regarding that, right? Yeah, I think you even tried Qiskit or Qbread. Which platform did you use? Yesterday there was a demonstration in the afternoon, right? Yeah, you used IBM Quantum Platform, right? So with respect to the IBM Quantum Platform, you may have already run some circuit which showed entanglement, superposition, and things like that. That is something that you would do initially on the demonstration. So with respect to quantum key distribution, there are a lot of challenges, because one thing that will be covered on the later stage of the talk is the decoherence. So QKD is still a niche area, but defense is very much working on this. Okay, like China, like the country which I have not mentioned, China is like when we compare other countries, China is very much focused on QKD. Like some are saying that it's a hoax. We don't know. Like in the research space, they are like aggressively working on QKD because they want something that other countries are not working on, and they want to future proof it like aggressively. But all the other countries, they are working on QKD, but they have not incorporated into policies. But here in China, things are different. You can see how the research is happening in that aspect. So the current QKD, like there are under the IIT Madras, from like IIT Madras to Bangalore, they are trying to have a quantum computing QKD network with fiber. They're trying to do that. So if you look into National Quantum Mission, like they're trying to connect various quantum hubs. So like here, IIT Madras based hubs are mainly working on the QKD side. So the inventory challenge. So this is something like when I talk to companies, like for me, I want people to sell the stuff to, right? So uh, they don't know why they use encryptions, what's the necessity. So when we try to talk with companies regarding to post quantum cryptography, like they are very much hesitant to do that because they are not aware about what is happening. And like all the legal frameworks, all the budgets, everything, like they have to change, and even the hardware that you use, they have to change. So like companies are very hesitant and they don't allocate budget in that aspect. So these are the two like large stakeholders, especially in the technology domain. One is the PQC mandate, like as I told, they had migrating around 2030, 33 around that, and EU is recommending to use hybrids. So the problem is that there will be a lot of problem in the hardware domain. So this is the thing that the risk is the like harvest now, decrypt later. Like you know about the attack, right? Harvest now, decrypt later. Like, are you aware? Like, I think, like, have you heard about harvest now, decrypt later? So I'll tell you, like, in simple words, what it is. It's a very simple thing to understand. Say that you have a safe, okay, which contains a lot of secrets, say financial data, something our sir have mentioned. So financial data is something that's stored in a box. We don't have the key right now, but still I have stolen the data. Okay, I have stolen and kept it later, so that when I have the right tool to open it, we can decrypt it later stage. So one thing that is the policymakers are very much scared is about the harvest now, decrypt later attacks. So it's that's why the bigger risk is that even if the information is stolen and it's still on not on a readable aspect, but they can do it later stage. So so the reality is, even if it's bottlenecked by engineering physics, we policymakers or academicians, we should like really work on understanding the migration and what is happening in this particular domain. So this is the first presentation. I'll switch to the next one. Uh, you can make it full screen. So we have talked a lot regarding cryptography. Now I have told that one of the bottlenecks that we have is decoherence. Decoherence, like have you heard the word decoherence before? Like at least not on a physics aspect, but decoherence. Like what does the word translate to? Yes, that is something. Yes, in the quantum computing concept, like it is that like decoherence means, on simple words, it's like the qubits that we have is losing its property, and it is changing its nature to more of a classical nature. The bits that we usually use, the one and zeros, and not the superposition ones. So why decoherence and why quantum technology? So the classical computers use bits 0 or 1, which have been repeatedly told in the previous presentations, like everyone must have told regarding that. And the quantum computers that we use is something called as qubit. Like how do we represent qubits? Like from the past presentation, like what have you learned? How do people represent qubits? Yeah, it's more of a matrix. It will be on matrix. It's basically a vector, something in a vector as, and so even the computation will be mostly based on matrix formalisms. So the qubits are like we use ket 0 and ket 1 for qubits, and it's just like we use matrix notation for it. So let's focus on the fourth point in the presentation. We'll be focusing on the fourth point because all the other three will be like already, like I don't want to repeat it again, all the superposition thing. So as we know, qubit is the basic unit of quantum information. Uh, so these things you may have already heard. Again, it's vulnerable to lot of noise and disturbances. So like have you seen the picture, like when you say, people say about quantum computers, like which is the picture that comes into your mind? Like all the posters, everything, like one golden thing, right? Something like a chandelier. So have you ever thought the purpose of that particular thing? It will be a big cylindrical tubular thing, and there will be like circuits with golden plating and all those things. It will be something like the chandelier that we use. It's one of the technology. It's not only that, is one of the technology that many prominent companies are using. Like have you ever thought of the purpose of that particular thing? Like what does that thing do? Like have you ever thought? It's called as, that particular unit is called as dilution refrigerator. Okay, you may have already heard that, but the dilution, like what do refrigerators do? Yeah, what do refrigerators do? It's basically cooling things, but here the fridge is more powerful. It will be cooling in the range of millikelvins. Okay, it will be very cool. Like the fridges that we have, like it's more cooler, of the order of minus 300. It will be around 370 degrees Celsius, which is very cold. So with respect to that, so that particular, why they need to use those kind of expensive refrigeration units is because of the decoherence. Okay, so the picture that we see is basically a fridge. Okay, the cylindrical thing that you see, it's a very big fridge which cools qubits to avoid, to reduce the decoherence and to increase fidelity. Okay, so the same thing. So the spinning coin analogy is something that we use, and this particular, in this particular scenario, when disturbed, it falls into like heads or tails. So similarly, when environment interacts, it again causes like disturbance. Okay, so understand that in the quantum circuit, like did you, like while using the IBM quantum framework, did you see the measurement gate? Like there is, to get the reading, there was a measurement gate. Yeah, that is how you see, like yesterday's demonstration you may have already seen. In the end you will see the probability, right? There will be like a graph in which like there are multiple states, like the probabilities of multiple states are there. So that is how usually the quantum computers should behave. Like did you like run it on a hardware backend? Did you do that, or it was just simulation? Like it was only simulation. So in the graph, it would be very like defined. There would be no noise. But when you run into the backend, it's not the case. Say that the probability is around, like we need to get around 50% probability for the state 00 and the state 01. But when you really run, if you can try it with QBraid or IBM Quantum platform, you could really try that. When you run on the hardware backend, you may have small probability on 01 and 10 also. Like you should try that. Like this is, so when we are talking things, it may not be very clear, but you could really see decoherence in action when you run on the real hardware. So there will be, if you go to the IBM Quantum platform, you can run on simulators, and then you can run on like processors like mostly everything is named after some birds. It's falcon, heron, eagle, and all those things. So when you run on hardware backends, you could see the noise even in the graph. You can like literally see the noise in action when you run on real hardware backend. So why does that happen? It's very simple. One of the thing is environment. Okay. So understand the fact that even a very small spike in temperature, the qubit translates into trying, like we trying to take a measurement. Okay. Like what happens when we take a measurement of qubits? It collapses into one state or the another. Similarly, when environment interacts, it does not, the qubit does not know whether it's a noise or someone trying to take a measurement. So when environment interacts, what happens is that the noise will make the states to collapse. So now, like when we talk about quantum advantage or quantum parallelism, decoherence is something that destroys and making the qubits powerless. Okay, so then what happens? All these things which was theoretically told, quantum computers are powerful, they are able to do a lot of material science calculations or say engineering calculation, or a lot of optimization problems. This advantage disappears when decoherence is in the picture. Okay, it's a very big challenge that we are facing. On that simulation demonstration, you will not be able to see that. But when we like really run on the back end, the computation becomes very much unreliable. It's like say that the speaker is having some kind of problem and it's interfering and I'm trying to talk. So what will happen? You'll not be able to hear. Or say that we are going to a market and trying to speak to each other. So similar situation will happen when decoherence is in the picture. So what is decoherence? It's a physics limitation that the current quantum computers is having, and it's a very big challenge, and it's something that you professors can really work on, especially if, like electrical engineers, like understand the fact that equal contribution is done by the engineers, physicists, theoreticians, mathematicians. Quantum computation is a collective effort. It's not like some physicists are sitting in the lab and doing that. There are electrical engineers who are sitting side by side working in the realization of this particular thing. So this is something, decoherence is something that is bugging engineers and scientists together, when trying to realize quantum computation. So it's very unreliable. Then the communication become either incorrect or not secure, because it will switch its behavior into a classical realm. So what is environment? So like when I say environment, we may not get the right picture. So it can be electromagnetic noise. As we know, the communication devices that we use, it's a large source of noise. Okay. So, and then there is heat difference. Like the dilution refrigerator is very much doing is to trying to avoid the heat problems, temperature problems. Then there are vibrations, which is physical, and then there are measurement devices. Like as we told in the demonstration, like for the real quantum computers, we will be using some kind of measurement devices. For photonic, it may be like it may be a photon detector. For uh, for a superconducting qubits, it will be a Josephson junction and things like that. And for ion trap, it will be vacuum based and a lot of things, which is again in turn source of noise. So this is something that I told when we go to market. What happens if we try to speak? That is something that happens. What we are trying to intend to say, it will never get communicated. This is happening in the, like, I understand that this is what is happening to the qubits. So the error accumulates, and as we know, when error accumulates, we will not get the intended results. So what happens? So one thing that is not mentioned here is that when we tell about the interactions, we also want to understand that there are multiple qubits here and multiple quantum circuits which are closely sitting in the processor. So what happens? Even qubits interact with each other. So see, uh, so it will be very difficult. So like, let me now go to the domain of quantum communication. So like the previous slides were more focused on the computation aspect. So again, as I told, here also the same problem occurs, and qubits are very sensitive, and there are various errors, bit flip errors and the superposition there, and it can be mathematically represented. If you are interested in the math, there is something called as the Krauss operator, which is basically a matrix which models the how the noise is modeled. Like it's just mainly it is usually either a square matrix or a column matrix, which depicts, like, I don't want it to be too mathematical. So Krauss operator is something that you can look on if you are interested on modeling noise. Krauss operator is basically a square matrix which try to say how the noise is acting on the qubit. So what happens? Like, we told a lot of things. So what happens? The quantum state stability is very less. Okay, it's stable for a very short period of time, which is very undesirable for a scalable system. Okay, so the problem is that coherence time is very less. The survival time of quantum states is something very problematic. So what is the problem? We have to do computation before decoherence. So it become a problem of time. So we have to find problems, or find solutions, or like program in a way, or try to understand the architecture and do the programming. Okay, because we need to go fast, otherwise it will decoher and it will not get the result that we are expecting. So the next question that will come into our mind is that, can we stop decoherence? So completely stopping decoherence, it's not possible. That's why we have error corrections and things like that. Then we can slow it down, and isolation and cooling really helps. That is where the dilution refrigerators come. The big cylindrical thing. For example, if we are using superconducting qubits, and that is why IBM and Google are very much focusing on superconducting qubits, because it have a very good feature of isolation and cooling. Okay, so there are other technologies. For example, photon-based technologies are there. That they can be carried out in room temperature, but the problem is that it is very much prone to the noise because there are other light around it. So it will obviously, there are photons which are intended to use for communication, and there are like particles which are interacting, and which it causes lots of chaos. So for superconducting qubits, we can isolate with the help of dilution refrigerator and proper sealing. So error correction is done. This is something that we do. But the problem is that the bottleneck here is that we need more qubits to do calculations. So then on a security protocol, protocol aspect. So how is communication taking part? Like how is, say, let's talk about some, let's drop the physics for a while. Like how do you communicate in WhatsApp? How does it work? Like they advertise it very much. Like how does WhatsApp communication happens? Like you don't use WhatsApp. Like what is like have you ever checked the top of, like, when some chat is starting, like you see something on the yellow, like it is like end-to-end encrypted. Have you seen that? Like they have they are aggressively marketing that. So similarly, so how does communication happen, secure communication happen? Say that there are two parties, Alice and Bob, and Alice is trying to communicate to Bob, and to avoid eavesdropping it will be encrypted, right? Even if we are sending hi, it will not be hi in the between. In between, it will be decrypted on the later stage. For example, what we have here, for example, WhatsApp have the end-to-end encryption protocol. So even if there is eavesdropping in between, what you see is some random message which does not have any meaning, right? So similarly, quantum communication is also operating in that direction, because communication is between two people. And so when there is a secure communication channel is established, for example, if you are connecting fiber optical communication, what happens is that we have to terminate communication if there is a hacker in between, right? If I'm trying to communicate from here to Delhi, and there is someone who is intercepting me in Andhra, say there is a hacker who is sitting in Andhra and intercepting my communication, so I'll have to terminate the communication. That's how quantum communication is secure. Like the eavesdropping attack, it's more secure because when in the channel we could see if someone is eavesdropping, because the state would collapse and the features like no cloning theorem will come into picture. Like if you quantum security is very much based on that. So eavesdropping happen, and so noise can also mimic eavesdropping. So like we are, yeah.
In quantum communication,
Uh.
you mentioned that encryption decryption will happen.
Yeah.
So encryption decryption happens in a classical way, or how is it?
We will use classical channels itself.
Okay.
Yeah, because there is nothing like we'll have to use classical channel.
Okay.
Yeah. So so that is another problem. Even if we are using QKD, we'll still have to use classical channel. Like there is say that the weakest part is the one determining the security, right? So the which is the one that breaks initially, that will cause more chaos. So as we need classical channel to establish communication. So the problem is that when there is an eavesdropping attack, it's there everywhere in quantum communication or classical communication. So we cannot understand whether it's noise or somebody trying to attack. So distinguishing noise, because understand the fact that we are trying to take measurement, right? Quantum computing, in everything there will be measurement in the end, measurement of states and it collapse and all those things. So the problem is that the problem is that if there is something called as there is an Eve, which is the third party who is trying to intercept the message, and he is the hacker, he or she is the hacker. So what problem is that we'll not be able to understand whether we have to terminate the communication because of Eve or noise, because both behaves in the same manner. So we'll lose a lot of resources in that aspect. It's very difficult to distinguish the noise and the eavesdropping attack, and it will cause more problems. So on the engineering aspect and the challenges, so the problem is that we have to, for superconducting qubits, we have to maintain low temperature, reduce engineering noise, and the engineering complexity of soldering a lot of things together which may interact with each other, which is not happening for the classical protocol. And scaling up it's really pain. So decoherence is a determining factor in that aspect. So we have to understand how we should proceed, how we can design the hardware, and how optimized should be the algorithms and protocols, because the better code means less problem. And so there is, in the engineering aspect, there is a lot of things on soldering, and the processor, quantum processor design is a very big difficulty because of all these noise and interference. And even like, so understand that we have the freedom of running any programs. Like say we are running a Python program in a laptop, it's possible. Okay, so when we do something more computationally involved, we may use a superconducting cluster, or we may run on the cloud. That is something that we do. There we have the freedom of choosing our hardware and things like that. But here, even for designing an algorithm, we have to think about the hardware. So when we are designing algorithms and protocols, we have to think about the hardware bottleneck. So that is something that influences the algorithms and protocol design, which is very difficult. We may not have the proper way to solve the problem. So this is something that is happening in the research domain. So there are in the material science aspects, there are research happening, and how to reduce noise resistant qubit design is something that we do. And then there is machine learning for error mitigation and hybrid quantum classical system. So the key takeaway from this is that decoherence is something that we cannot avoid. Wherever there is quantum communication and quantum computation, there are limitations because of this decoherence and error. But we have to, when we are thinking about the architecture or trying to design algorithms, we have to very much understand how they work, and we have to find a way to manage. So yeah. So if there is anything to ask, we can ask, and we'll go. Yeah.
Yesterday also I was just asking.
Yeah.
Some attending the sessions continuously.
Yeah.
Can we have to know what is the simplest method to implement a simple SOP and POS form of the equation? Simple, A plus B or A dot B, I want that.
Using quantum computers. I don't know that particular thing, but I'll try to understand and get back to you.
Because yesterday also they said it requires lots of gates. They were just teaching how to implement the gates.
Okay.
You know the gates working.
But you need to do it for a usable program.
For a usable program.
Yeah.
I have got many work with the optimization and meta use algorithms which are available.
Yeah.
Where my equations are going up to thousands.
Yeah.
Order of the thousands
Yes.
I'm having.
Yeah.
Summation I got summation xi is starting from 0 to 1000.
Yeah.
Xi square.
Yeah.
So obviously the computation will go up to 9.
Okay.
And I need to know at what rate I'm going to get an optimal solution which can converge.
Yeah.
That is one of the problem.
For computer science, this is something that SOP and POS is something that we do right in the beginning, and this is something that
This is the basic.
Yes, a basic thing.
Whatever the other problems, whatever we are facing, that will come at the later
Yes.
stage. we need to understand how we can implement an SOP form,
Yeah.
because functions, no
Yes.
one is being able to give you the clear idea how we are implementing that part. Yesterday when I went home and I did some research on that part,
Okay.
it is giving me 500 lines of program. That's what I just 500 lines for just one SOP. Then why you are going for the quantum now?
Yes. So that is something, that is one of the misconception that we have. Like everything will not replace the classical computers. That is something, like one of the perceived notion, like one of the problem is that like people are thinking that quantum computers solve all the problems. That is how it's propagated, and it's a very wrong thing. So wherever we still don't know, like I work mainly on decoherence. Like I don't, I have very less programming background. So we, like, I tried to, like, my research work was mainly mathematical, where we tried to solve the cross operator, and in the end we tried to model the fidelity. That's something that I worked on. So like I had very less programming. Like the graph that I plotted is mainly based on Python. So what you have asked, the question is very valid. So my answer is that some part will be like existing in the classical realm itself, but some of the difficult problem for classical computation, like it is not the answer for your question. Like I'm like clearly stating that, but as you said, there are problems which makes optimization problems and computation problems, which is using quantum computers too easy to solve. So
There are many algorithms which I
yeah.
work with the meta-heuristic algorithms, where I come across many. There are hundreds of equations also,
Okay.
which can be solved by the quantum,
Yeah.
but not getting the proper way to get into the
So because we still, there are a lot of things
quantum functions, they are not have been implemented.
implemented. Yes, right.
Everyone is just saying this is the basic gates are available. S gate is there, T gate
See,
is there. The behavior of that gate
yes,
we
yes,
know.
yeah,
We have understood how
Yeah.
the gates are behaving,
yeah.
but how do we convert the
Thing into that.
a
Yeah, yeah, yes,
equation?
yes.
Quantum equation, how do we implement? How do we connect the gates for the, because we know the what is happening.
Yeah.
We know the mathematics behind. We have to understand the linear
Yeah.
algebra part also. We know because of the.
You are telling about the usability.
Yeah, we have understood that
Yes.
part.
Yeah.
But from the mathematics
Yeah.
part, now I need to implement the hardware.
Yeah.
I have to know how do I simple equation can be converted.
Yes.
So, for example, if I'm just taking a simple half adder,
Yeah.
I know that in the half adder I'm having a and b 0 0 0 1 1 0 1 1.
Yeah.
When I simplify this, sum is going to give me a x or b, and carry is going to be a dot.
Yeah.
How do I implement that a x or b here?
Okay.
How can I implement a dot b?
But even if we are using the analogy of the gates that we use in the Boolean algebra, and it's different here. Like
That I know, but
yeah.
we know that in the
You are trying to
classical.
you are
In
trying
the classical, we know.
Yeah.
This is the thing. I have got
Yeah.
a Karnaugh map is available for me.
Yes, yes.
Which can solve me. Which can give me minimum terms. I have got,
min terms and max terms. Yeah.
max terms are
Yeah.
available, which can give me the optimal solution for me.
Yes.
But in quantum, I am not able to find any of these kind of equations which can give me the simplified equation.
Right. I get your point. Yes.
Yesterday it is just blocking my mind there. Not able to. How do we simplify the complex equation
Yeah,
into a simple one?
Yes.
And yesterday also I was just doing some research there. But there also the given the equation, the final answer is available.
Okay.
The steps in between, how we are converting that. What are the steps need to be followed to convert a classical equation to a quantum equation?
Yes.
If you can just highlight if you have knowledge on this.
No, I don't have. Like I don't have an answer to that. Sorry. But that is something that if I have something, I'll share with Shreyansu. I'll get back to you. I don't have any idea. Like I got your question, but I don't know the answer. Yes.
Most of the people are want to do PhDs and all research work.
Yeah.
So which one you recommend? You mean to say quantum computing or quantum communication? So you mean to say as a layman, see, because we know that it will not become an interesting. Yeah, I know that. So they based on their interest, but the thing is, according to your experience and your knowledge,
So yeah. Uh, so our sir has, sir, what is your name? Srinivas sir have asked the question, like, which is the PhD domain that, like, anyone, like, is there any recommended domain from my end? So I'll just try to say what are the fields that are happening in the quantum domain. So one, the theoretical framework, when I told about the Shor's algorithm and things like that, there is a part where theoretical physicists and mathematicians work. So someone who is from the mathematical background, they can work on that particular domain. So I worked on theoretical domain where my work was mainly solving matrices and trying to make a sense of it. And sometimes I get lost, like after 6 or 7 pages of derivation, I may not get anything. So some of the days were like this. So those who are very into theoretical physics, like maths, the abstract thing, there they don't think about the photons, nothing. They don't think about anything. Many of the things will be based on, like calculation. Some will be pen and paper. Some may use like computational tools. So those who are interested in that domain, they can work on that aspect. Some may be interested on the engineering aspect, the sensing, metrology, materials, all those things. Those who are into material science, they can work on, like there was a time when everyone was focusing on nanotubes, nanotechnology. There was like 10-15 years ago, if you see, like even like engineers and physicists, they were very much working on like the fullerenes and all those things. So here, like the material science, those who are into that particular domain, they can work on developing materials which make better qubits or qubit system, like to make the architecture better. And the other thing is the electrical engineering side. Here they are using, for superconducting qubits, they are using uh, obviously superconductivity. So the electrical and electronics engineer, those who are very much interested, can work on that particular aspect. So and there are computer scientists also who design, like what the question asked by the professor here, like what he had told is mainly worked by the computer scientists. So like everyone have space. And even in qubit technologies, there are diamond based qubits, there are photon based qubits. So those who have expertise on photonics, they can work on photon based qubits. Like if you are interested, like IISc is having research groups which are working on even various qubit technologies. Like they are trying to realize qubits, like each have its own merits and demerits. And there are companies like QP, and there are a lot of companies who are working on the hardware. So for someone who are interested in like hardware, they can work on that direction. The theoreticians can work, like everyone have their own space. It's not like one should work, like I cannot recommend one domain is superior to the other, but it very much aligns on the interest. Like there are physicists who work on quantum optics before, but now they are trying to find application like quantum optics in the domain of quantum computing. So for senior professors who are working in like various domains, what they do is that they try to direct their research in that particular quantum computing application. That is something that people are doing nowadays. Like there are a lot of research group who did quantum optics or who did superconducting engineering, but here the application will be based on what like quantum computing, or even some photonics department works on QKD, satellite based, like Bangalore is the very right place where you can explore a lot of things, because there is Raman Research Institute here. You already know, you may have already heard about that. Raman Research Institute is working on satellite based quantum key distribution. It's not a single effort of physicists or something. The ISRO scientists, it's a tie up between the Raman Research Institute and ISRO. They work together to establish satellite-based quantum key distribution. Professor Urvashi Sinha is someone who is working on, like you can see her work, and there are a lot of others. She is actually chairing that particular domain. So it very much depends upon the interest. So for computer scientists, they have their own interest. So it's a collective effort. So and more than that, like when we talk, like it's not a sprint. This is more like a marathon. Like everyone running together and collectively trying to bring a result out of it. For doing PhD, it very much depends on what they want to do. Like I am not very much of an experimental person. I like abstract things. So that depends upon the student's interest. And like if you have students who have that, like feel free to tell them to contact me. I can.
In artificial intelligence and machine learning space.
Yeah.
So how so any quantum
There is like even in that there is something called as quantum AI, QML, and all. It's relatively newer. It's less mature than even this domain is having its own problem. It's more because like in the end everything comes to usability. As our sir had told, like some of the things that we are working already, it's working beautifully already using classical computation. But there are problems which are using. So quantum machine learning, there is a domain like that, but it's very much in their early stages. So there is something called as QML, and there are groups which are working on that particular direction. Yeah. Like usually when is a tea break? Yeah. I have like one more presentation that we can do after. Yeah. Yeah.
One request is we have
computer science. So, as I'm working on the education aspect, so policy and also the institutional readiness is something that we should be aware of, because there will be a lot of stakeholders even in this room. There may be professors who are heading departments, or deans, or those who are part of the senate or university association, or things like that, or with the connection of industries. So this is more of this will be focusing on more policy education and institutional readiness. So why policy is very important? We have covered, like it's the third day, right? Yes. Third day. Fourth day. We have already completed 3 days. So you may have heard a lot of things in the domain. So why this particular even the program happened under AICTE? So that's something that is being influenced by policymakers. Okay. So why we need policies which support quantum computation? So it's very much connected with the information processing, how we perceive information. So it is going to make a phase shift, but it will be taking some time, but still there will be change, and the policymakers, including academicians, should be aware about what is happening in this domain. So it's like when transistor came, then like circuit integration came, then VLSI came. So stakeholders were a part of a lot of things, and its impact of quantum computing is into a lot of domain. So the thing is that one of the challenges, so let's my talk is completely focusing on the challenge. So here what is the problem is that when companies make budget, they will think, say that you all are a founder of the company for now. Assume that you are a founder of the company now. You will have priorities, right? So you will initially focus funding for, say, you have to keep your employees happy. So what will you do? You will allocate fund for salaries, definitely. Then say you will give some funding for research and development. Then there will be operations. Say you are running a big company, you need infrastructure, you need to pay rent and things like that. So in the end, so the companies will think that why do we want to fund a long-term thing? We don't have that kind of money. So they give very low priority. This is something that, like when I talk with a lot of industrial stakeholders, like I have talked with the IBM research team, and I have talked with banking people from banking sector. They don't care about something's going to happen in the future, even though it's relevant. So this is something that is a challenge, and we need decade investment. It's a long-term thing, and there should be policy influence. Once, there are people who wear helmet for their safety, and there are people who don't care about wearing helmet, even if it may cause a fatal accident. But what did the government do? Government strictly imposed a rule that you will be fined. So similarly, here the policy won't be so aggressive, but still there should be some kind of industrial utility policies so that they can migrate gradually to post-quantum cryptography. So we have talked a lot about the scientific perspective. I'll not be repeating that again. So one thing that bottlenecks is they don't know what is happening in this domain because it's too technical for them, the policy makers. So they don't So some may be completely unaware of what is happening, which cause them not to invest on these particular things, and some may not care about this because it's too futuristic. So metrics is something that is another challenge, because when we say qubit count, this is the reality. Okay, the 100 perfect qubit is better than 100,000 qubits or a lot of noisy qubits. So then the reality, so they don't care, like they don't understand how impressive it, they just don't. Scalability is one of the problem, and the cost is another problem, because there are a lot of things that can be that can be made use of, but it is not happening. And there are like this is a controversial statement, but still so one of the things that is a problem, people working on fundamental physics or fundamental sciences, whether it's mathematics or computer sciences, those who are working on that is getting reduced. So even this is a roast on myself, but still, so there are cases where like there is a lot of hype and there is no real work being done. So that is another reality. So people neglect all these things. Like I don't want to repeat it again because of the time constraints. So there will be a point we have to forcefully do this, but it's better to be aware and gradually migrate. So let's skip this. Yeah. So this is something that is another challenge on the. I have told about harvest now, decrypt later. See, this particular thing, when CRQC, I'll expand CRQC, it's cryptographically relevant quantum computers, which is not existing for now. But when they arrive, this particular attack become very relevant. I told about this analogy where we are keeping a secure box which it is still not able to open, but on a later stage we will be able to open when we get the proper key. So there is a challenge thing that is happening, and moving to post-quantum cryptography. It's a large logistic task. So companies and policymakers in companies are very much lazy on doing all this heavy work. So they don't care about doing all this, and they tell that let it come, let the cryptographically relevant quantum computers happen, and then we'll do all these things. But the reality is that whatever we are saying, it's only the 10%, but the 90% should be happening from the companies or the industries. And so there is a lot of asset management and inventory management that need to be done from the industrial perspective. So the banking system have a larger life cycle, as we have discussed when we started this conversation. So it will have around 30-year life cycle, and if they are not probably aligning the policies, it will be very difficult. Even like I told about talking with people at IBM Research. So what they told was that they were telling that, like when we talk, like IBM is a very big company, like even the platform that was developed and being used by academia, industry, the IBM quantum platforms or the IBM quantum labs, QSKIT and all those things, they have created a big infrastructure. Even for them, when they talk to banks, they don't care about all these things. Like I've talked with engineers from IBM who have told that not only IBM, there are like from startups, I have my colleagues and other friends, they have told that they don't care about all these things. So they are waiting for the quantum emergency. So let quantum computing come and we will do the migration. So so the thing is that when they think about the next budget, they don't care about it because there is only a smaller qubit volume, usable qubit volume. So they don't care about all these things. So the role of standardization body, as I said before, NIST, ISO, ETSA and all these bodies, they are trying to bring some kind of mandates, and gradually they will force the companies to migrate, and it is something that happens. So until the mandate comes, people don't very much do crypto agility, and they don't care about all these things. So so what they do, so one of the things that they need is there is a centralized quantum office kind of thing with real influence that can influence policies, and it should have clear security and IP frameworks. So, and then the other thing that this is a very big reality, especially when I talk, I have talked with a lot of, I have been to colleges, especially interacting with students. So one of the problem that is there is that they are not aware about what is happening in the quantum domain. Okay, so they should be very much aware about what is happening, what we have in the something similar, that kind of culture which should happen in the domain of quantum computing. So this is something that need. The current curriculum don't very much talk about emerging tech like quantum computing. So it should teach even initiatives like this, ATAL, it's something like that should happen in the curriculum level even for CS or other engineering students. So curriculum gap is something that is there when I go through the courses in quantum computing. Yeah.
So as you mentioned, the policy doing something. Is it anything is needed from a business perspective? That's why the business people are influencing the policymakers, so that the quantum computing will be.
So one of the thing is that government should give some kind of directives, unless they won't. Governments or standardization bodies. It's not.
That's correct. So the government is. You mean to say, is it the business? See, most we know that the politics will be run by the business team.
Yeah.
So is it any business problem is arriving in the future, near future, maybe security?
Yes.
I don't know.
Yes.
So maybe because of that reason.
Yeah. So the problem will be the data which is being only stored for 1 or 2 years is not vulnerable to these kind of attacks, because we don't have quantum computers which is able to break all this security. But at some point, legacy system which need at 30 years data store, those kind of organizations should have some kind of policies to quantum resistance, PQC at least they should have. Say that I am storing the data for an event like this. People there will be no point in storing it for 5 or 10 years. There is no confidential things. So for companies like that, it will be important. But there should be standardization and there should be policies influencing that. Not all everything as I said before, not all problems need quantum computers to solve. We can use classical. So similarly, policy should not the government or the policy makers or standardization body like ISO or NIST should not say that everyone should use quantum computers for them. There is no point in that. But where there is relevant, there should be some kind of guidelines or mandate. Otherwise, it would be very difficult to migrate on a later stage. Yeah. So so this is something there should be for quantum computing especially, there should be some kind of interdisciplinary there are interdisciplinary approach being done, but I still think that especially when I talk with CS people from CS department, especially those who are less exposed to quantum computing, one of the things that they say is that there is too much physics in this. So we don't want to study this. So it is not the fact there is a lot of space for CS people only, like things that physics people don't understand, but they are not aware of the fact that like quantum computing, here what quantum meant was quantum computing. Like quantum computing need people from CS and all the disciplines to work hand in hand together. So, and there are other things also, policy perspective, physics people may not be aware about what laws and what regulations should be there. So we need engineers who are aware about all these interdisciplinary tasks and who work exclusively, and there is something called as full stack engineers where they do front end, back end, or all the stack, but some may focus on back end or front end. So here we need like what I meant by quantum system engineers, there should be people who are aware about all these things, whether it's physics or the computer science or even the industry standards and things like that. So we need people like that, and the other thing is that it should not very much focus on one particular institution or a very small part of the research group or a very small collective. It should more be like a diverse collective where a lot of people are working together for a particular goal. So this is something, again, like people, like when we talk with people who are not working in the quantum domain, so people really say, even for blockchain, you people are scamming. Because there is, for example, in the blockchain, you may connect to that particular domain more easily. So blockchain, there'll not be anything related to blockchain, but simply they'll be branding blockchain. There are companies who do that. So the problem is that who are genuinely working on the blockchain also labeled as people who are working like they are scamming others and things like that. But like blockchain is something, Web3 is something promising for the future. So similarly, also this is something happening. Randomly people putting quantum on everything, but it's not necessary there. So what happens is that people get misunderstood a lot, and real good educational initiatives, it's a very difficult thing to approach. And okay, so this is something that is happening. I told about Marvel movies, right? So when like there is a narrative that there is infinite speed, and like there are, if you like are an enthusiast of science fiction, wherever there is things like this, people randomly tell that this is the power of quantum physics. So the real technology aspect, what is happening, it's being buried in all these fancy terms. So it's a false, it gives a false sense of what really quantum computing is. So people have misunderstood a lot about this particular domain. So there should be like a policy or at least there should be some kind of unwritten rules in a way that when we tell about quantum computing, it's really quantum computing and it's not some random terms which makes no sense. So, okay. This is something, the quantum supremacy. So there is a competition in between companies. There is a lot of ego and a lot of things happening. So they branded the quantum supremacy and other things, quantum advantage, a lot of things. So it's a milestone, but they have branded it into in a way that okay, we'll be the market leader who do this first. So there is no collaboration, more of the competition. The analogy that I told, like people, like every company is competing to find a usable quantum computer, but the problem is that if they work hand in hand or collaborate each other, they could work better, but that is not happening. It's more of a competition. But at least in the academic space, like it's been continuously told in the events, like in the National Quantum Mission events, one of the events that I attended, like it's not like which research group or which faculty publishes more in this domain. It's more like let all faculties work together, research group work together to make something on the usability. Like on an academic perspective, it can be done. But for companies, I don't know whether they'll cooperate with each other. I don't know whether there will be a point where IBM and Google and say Xanadu or Rigetti, all of them coming together and working together for a usable quantum computers. Because what they think is more of the like if we bring the technology first, we'll be getting paid more and we'll be selling more. So that is something they are focusing on. On the other hand, academicians like you or people who are closely working with industries, they could align the work together and more the merrier, right? Like it's like parallel processing. If a large number of collective is working together, we'll have something which can make use a utility based quantum computation, or there will be real quantum advantages. So then there is ethics. Then okay, so this is something that is another thing. We know like not everyone should be physicists or engineers who are working in this domain, but they should have some kind of understanding when there is policy making. So this is something, ignorance lead to either over regulation or under regulation. Both have their own disadvantages. So let's talk about more on the policy side. So there should be timelines, there should be policies based on like the logical qubit count. Like there is already a roadmap by a lot of companies where they'll reach at 2035. So they should have, we should have policies in a way that the hardware moves. So there should be like multiple possibilities where like understanding quantum computing, and there should be infrastructure which is working on multiple perspectives. So not only cryogenics, we need optics, we need like say ion trap based qubits. And so I'm going to the conclusion part. So education. With the education perspective, say that at least every college should have like at least a few people who know what is happening in the quantum realm. Initiatives like this, like whether it's faculty development programs or some kind of interdisciplinary group, should be very good in each institution. All of the prominent institutions or universities are having some kind of quantum awareness now. It's a very good thing. Then standards like NIST PQC guidelines should happen. Then inventory, like companies should be aware about this security risk that is happening. And also funding, like for everything, like as you know, research or building infrastructure definitely need funding. So we need like, this is something that I told. Let me conclude. We cannot this is the ground reality. We cannot know when the first usable quantum computers. There are quantum computers existing, but usable quantum computers, we cannot predict a correct date or a time where it will become. But we can predict what will happen when the first usable quantum computer is happening. So and then vision should be there. So on a strategy perspective, people should start working on crypto agility. Then on a long term, there should be a workforce development thing, something like, so for education, FDPs are happening. So companies also should develop a workforce which know, where there are engineers who know what I have been telling for the past 1 or 2 hours. And also there should be a common international standards. So NIST is being maintained by the US, European Union have a separate body, India have a separate body. So there should be a common point where they meet and there should be an engagement in that aspect. So on a concluding note, the hardest part of quantum computing isn't the physics, it's more of the people. It's more happening, whether it's education or whether it's policies or whether whatever we have, like even if there is a lot of physics and engineering, whether it's computer science, electronics or whatever is there, it should be more focusing on the people aspect rather than the technical aspect. Even though technical aspects are important, people should be aware, and like in all aspects, whether it's academia, whether it's industry or startup, like or the common public, we should have, like there should be a platform where people could talk about all these things, which is something that I'm trying to do in the company that I'm currently working on also. So we focus more on like interacting with communities, how they perceive quantum computing, and try to understand, like make them understand what is happening in this domain and move further. So I'm concluding now. Like you will have some time to interact with me, and then there will be an IB, and like the place that you are visiting, it's one of the like say Center for Development of Advanced Computing is doing some good work in quantum computing and communication. You can interact with engineers who are working on that. I think there are two in Bangalore. One is in Electronic City and one is the one that you are visiting on. So you could really understand, like I have told from my startup and academic journey, so you could really understand what is happening in the industry. So you will meet project engineers and project scientists who are working on this domain. Sir, there will be interaction, right? So try to make use of it and try to understand what is happening. And even C.dot is working, telecom related quantum computing work. They do have a group there, and I think C.dot is also based on Bangalore, I believe. C.dot. Like CDAC is another government body who works extensively on telecommunication research and engineering. So if you are interested how industries are working in India, you are on the right place, because Bangalore is one of the happening place in the quantum computing domain, and another government based initiative aggressively they are working on for Karnataka. They are working on QCity, which is connected to Bangalore. And the Andhra Pradesh government is also doing something called as Amravati Quantum Valley. So they have been a lot of attention. There was a lot of press attention when the chief minister of Andhra told that they will give 100 crores to someone who get a Nobel Prize in quantum computing. It cast a lot of press and controversies. So they are aggressively marketing and doing PR, and they are doing good research work. They are collaborating with industries. Obviously, for everything they need some PR and marketing, because otherwise it won't reach the right people. So again, and Karnataka government is doing very good works related to QCT. And on an Indian context, the central government DST is also working hard with universities. The National Quantum Mission is initially focusing mainly on collaborating with institutions, because there is a lot of researchers and good talent pool there. So a lot of initiatives there. I hope you can look on to that, because Bangalore is one of the thematic hubs under National Quantum Mission under IISc. And with respect to quantum communication, it is IIT Madras. So you could try to attend the programs and try to give research proposals or grant proposal when relevant, and do, because they are mainly collaborating with institutions. So you professors have a very good possibilities of collaboration, and like bring, like even there are now faculty founded startups. So it is something that you can work on, and the government is very much promoting that. Central government have schemes for faculties, for faculty founded startups. The state government will be having like corresponding counterparts, but you could really work on that and try to understand that. Yeah. So that's all. If you have any questions, I'm here, and that's it. Thank you.
So, are there any opportunities for the students to learn about the quantum?
Yeah. So there are a lot of open source resources. One is the IBM QuizKit. They have very good tutorials. QuizKit tutorials are there. Then there are like programs, boot camps, workshops kind of things which will happen. Even we will be conducting as part of my startup. And there will be also, so as Shreyansu have mentioned before, Pennylane also do have some good tutorials, and QBraid is another one. There is a lot of startups and companies who have technical documentation and videos. But one of the best community that I have seen is the QuizKit community. There is a Slack channel, like you faculties can also join that Slack channel. There is a lot of discussion happening. Okay, QuizKit community is something that is like, as it have more volume, more people are there. There is a lot of discussion happening and a lot of resources there. That is something that you can check on. And there are a lot of, CDAC have something called as, the one that you are visiting, there is something called as QUniverse. QUniverse is a program under CDAC. That is something you can check on, and CDAC continuously organize free workshops. And there is a lot of good researchers based on Bangalore, Pune. Pune is one of the place, one of the CDAC, I believe they are also working on quantum computing. CDAC Pune, Bangalore and Pune is place. They conduct a lot of workshops and programs. So there are very good free or low cost programs conducted by these people.
What are the internship opportunities for the students so that they can convert that into a job?
To be honest, it's a bit difficult to get a job in quantum computing right after undergraduate degree. That is the reality.
Then join as an intern,
Yeah.
learn, and then that can be converted.
Definitely in the software domain. Software domain there is very good possibilities. Like it can be like startups or industries, but it's still really on the early stage. So we cannot compare AI, like AI kind of placement in quantum, but there are definitely internship opportunities. CDAC take BTech graduates. They take project associates from BTech background. So the hierarchy is something like this, I believe. There are project associates, which are basically BTech people. Then the project engineer will be like more higher than that. Then there are project associates, so a project scientist and project engineer, something like
So
that.
is there any specific prerequisite for the student to be selected as an intern?
Interns, there won't be much strict rules, but for engineers they will ask some background in quantum computing.
What is the basic background that will be required for this? They have to go.
For internship, they should have very good mathematical background. That most people will ask about how well versed they are with linear algebra. That is something that we study on engineering colleges. Nothing. They have at least two or like in some university it's 4 mathematics paper. What about this?
We have 3. Now it has been 3. Earlier it was like 4.
4, so they almost cover every mathematical tool required. There will be matrix formalism and things like that. Most of the companies will be asking for linear algebra background, and some may ask about basic understanding about QuizKit and other quantum libraries, which is being the Google have CARQ. It's a framework by Google. It's again Python based. IBM have QuizKit. Then there are some other Microsoft have Q#, which is based on C#. So they are not Python based, it's C sharp based basically. So they may ask for some background in that. So that's what, for interns it won't be very strict, but higher level they will ask. Like I have attended interviews like in CDAC like a while ago, so they were asking about like the recent research in the domain. Like they asked me about optimization problems and things like that, like what is happening in that. But that will be for project engineer and all kind of role. The earlier ones, it will be less strict, but they will like the filtering will be based on basic programming tasks and all.
Thank you, sir, for the wonderful session. I request Dr. Mohammed to kindly present the token of appreciation.
Thank you so much for spending your valuable time. All the way he has traveled only for this session. Otherwise, he will be very busy since he has his, a lot of other things related to his company. Well, so we are winding up a little early, right? So we have another half an hour time, maybe another 20 minutes of time we have. We are waiting for the lunch also. Maybe at sharp 1 o'clock we are going to depart from the campus, right? 2 o'clock the session is going to start at CDAC campus, right? So I request each one of you to just to finish the lunch quickly, but the lunch it to come and it started at like 12:15 we'll start the lunch. But before that, as per the AICTE requirements, we need to discuss some research articles also, right? We will share one paper with you now. Soft copy will share it in the group. So make your team, right? However you want to sit. You need to fill one summary, right? And hard copy will be given to you. Where what is the objective of that research paper? What is the outcome? So a lot of input we are asking from your side. Okay, you use whatever the ChatGPT tools you have, but you go through the paper and write some gaps, some outcomes. So proper format we have made it for summarizing that paper, right? You can have a group discussion. Feel free to sit the way you like to sit here and complete this task. Madam, kindly share the paper with them and distribute this summary sheets with you. In fact, this is the activity which is initiated by Dr. Manjunath Kaunte sir, Dean Academics. Since we were busy with some other meeting, I just came out from the meeting, I have to go back and attend the meeting. So in fact, it is his initiative, and he has worked a lot to make that summary sheet also. And the outcome of this FDP, it is not only the knowledge which you are gaining, it is not only the hands-on experience whatever you have gained, it is also to get some research gaps, some problem statement you need to take it as a takeaway from this FDP, so that the learning definitely it will happen, we will continue this journey, and at the same time we need to start working on the research also, right? So this activity will help you, and one best thing what we can do is we will share all these summary sheets, back in the group, okay? So what others have given their input, that also we'll share with the entire group. You can pick up some problem statement from that and start your research, right? So please continue, madam. And share this one. Like last time I told, make a group. Okay, each group can have a discussion, and after that you can write in this as comments. Okay. You can take some input. Can you give some input on this? We'll just wait for another 15 minutes for lunch. You are forming and according to that I can change. Last.
You want us to end the stream, then pause it.
Madam, go.
Soft copy I have shared already in the group. You can go through that, make a team and have a discussion once you read it, and kindly fill in this form what I have shared.
So this is one paper you shared?
All five I have shared in the group, sir.
Okay.
Sir.
So each should be filled.
Each might have got different papers. I have shared already in our ATAL participants group. It is coming. It's coming. Loading.
Yes.
coming. I have shared. It will come in another. Have a discussion with them. Done. It's there in the group now. Please check it. What? Audio. Soft copy I have shared. Who has got survey of important issues in quantum computing and communication? Note that one, sir. This is different. You can go through it, you will try to understand what are the important areas they are covering. At least you will come to know the area of research in this field. No, you can take.
We can